All right. Well, hello, welcome, week 9. Hope you guys are doing well. I have updated the group sign-up page to now have sign-ups for final presentations and an extra credit opportunity for week 10 presentations. Okay, so next week on Friday, we'll have I have 7 time slots, 1, 2, 3, 4, 5, 6, 7. And if you sign up, you can your group can do a 5-minute presentation, and I think it's fun for you to see like things that the other groups have done. And if your group does this, I'll give you 5 points of extra credit towards your final project grade. And so that's that. So talk to your group, your teammates, and sign up for that. And then as far as final projects presentations go, these are the different time slots. So I've got during week 10, I've got Monday, Wednesday, Friday. So there's no class during week 10, okay? So, or at least Monday and Wednesday. So week 10, Monday, no class. Week 10, Wednesday, no class. I know, like, I would say take these time slots. And if you to incentivize finishing the project early and going early, I have put in extra credit for those who do give their presentations during week 10. And then if you want the extra time to work on your project so you're done week 11, you can totally do that. There's no extra credit for going in week 11. So sign up for time slot. It's an hour long. Basically, your group will present your reports for about 5 to 10 minutes, and then the other 40 to 50 minutes, like 50 minutes, I will read through your report very carefully, line by line, and ask you questions about your report. Okay, and that's and then I will grade it right there. So you'll get immediate feedback. It is. I am not trying to be. I guess just a heads up. I'm not trying to be super mean or harsh or overly critical, but I will ask, I think, questions that are relevant, and sometimes those questions will be tough, and the answer might be, oh, we just never thought about that. Okay, and I'd rather an upfront answer of honesty rather than trying to spin it and come up with some kind of excuse or something. It's you kind of think of it as like you were hired by some, to do almost like some consulting work, or you were, or you have to do a presentation to your manager at work, regarding the findings of your data, and they will. When you do this, your client or your manager will likely have questions, and you want to be able to answer or justify your decisions, as much as possible. And so that final project review, I hope is also a learning opportunity. So anyway, talk to your groups and sign up for a time slot. It's first come, first serve. Sign up for a week 10 Friday. I would just sign up. Okay, extra credit, all right, to kind of incentivize that. I don't know. Is that motivating? I don't know what motivates students to do things. So, yeah. And then regarding final projects, again, there are lots of different kinds of analysis techniques, way too much to cover in just one introductory class, and probably even way too much to cover, even like if you are a data science major and you have, you're studying this stuff, I guess, well, you're in school for 4 years, but, probably 2 years dedicated to upper division stuff. Even that, I don't know if you can cover everything. And I have, I've been learning statistics for years, and there's so many things that I don't know still. So, but I do feel like I know a fair amount. And so if you come to office hours and you say, hey, this is the question we have, we're trying to figure this out, and can you point us in the right direction, or tell us what kind of test we need to do, or what kind of analysis or what technique we should use, I'm happy to at least give you my thoughts and opinions and guidance there. Okay. So that's that. I don't know, any questions about how this is going to work?
For the Friday presentation, we're on that page yet. The Friday presentation sign up, 5 minutes, do we have to create like a PPT or something?
Yes, so you will create a PowerPoint or a slide deck or something, some kind of, it doesn't have to be a PowerPoint, okay? Basically, you're gonna bring your laptop and plug it in, okay? So you need to have a USB-C, because that's the adapter we have in this classroom. So I think most computers have a USB-C video out these days, but if your computer's like years old and it doesn't have that, then find a teammate who does, or borrow one from the library. And yes, you'll plug it in. You'll need to have some kind of visual to go along with your presentation. Does it have to be a PowerPoint? No, that's probably the most common visual aid. But other groups, I'd say 90 whatever percent did PowerPoints. But yeah, some groups in the past, they recorded a video, or they had like an interactive thing where they could kind of update the chart and stuff, which was kind of cool. But the main thing, is present your findings. And I'm more interested in your exploratory data analysis than some kind of visual thing that's going to try to impress me. So a PowerPoint more than adequate. But yes, you do need some kind of visual aid. Yes.
But for the final report, the presentation we're going to give within the 15-minute time slot.
Yeah.
We also have to create a visual presentation.
No, you can. That's not required. So if you do this week 10 Friday thing, you could just put that during your final presentation. Maybe add a couple things, go into a little bit more detail. And things like that. So,
will you publish a rubric?
Yeah, I will publish a kind of a final rubric. Anytime you have there is a subjective component to all of these things, and it's difficult to fully quantify. I don't know, in your writing classes, do you get rubrics for all of your essays, or is it kind of
Sometimes I feel like there is a rubric, but the rubric it's very subjective. For example, what counts as fully describing.
Yeah, it's a little bit based on vibes too, right? So there's a little bit of that, and so that's why I like having the meeting, because the first couple times I did this, it was just submit your projects, and I would read through it, and I would have all kinds of questions, and it felt very subjective on my end. And then so with the meeting, if I had a question, I could kind of go back and forth with the group, and then really kind of figure out was this fully investigated or not? And so that was so I do like having that meeting where I can kind of go through and ask questions. So I'll do my best to give a rubric, explaining what it is that I'm looking for, but But yeah, everything is a tiny bit subjective. We try to minimize, subjectivity, but some of it is, it's not possible to fully avoid there. Okay. Any other questions regarding projects and whatnot? Okay. Document your group meetings. I hope those are, I know documenting group meetings can be annoying. And the reason why I'm requiring it is to ensure that you are meeting as a group. If you're faking the meetings and just like writing up fake meeting reports, that defeats the whole point. I think, and I hope this is not one of those group projects, but it might be for some of you. But I imagine in high school or in other times, we've been part of a group where not everybody, or maybe maybe one person carried the entire group, and that's often a very frustrating experience. So my hope is that by requiring these documented group meetings, you're at least showing up together as a group and at least being able to accomplish some stuff. Okay, and then if the group meetings are work sessions, those are often productive, I hope, to get things done. I know those are also the ones that are hardest to kind of schedule and make sure everybody's on board with working together. But I don't know. Group project dynamics are always a little bit tricky. And that's going to be true for the rest of your life as well, when you're working at work and you're most likely going to be part of a team. And the hope is you're on a team of people that you like to work with and trust, and everybody carries their own weight. But unfortunately, it's not always the case. All right. Okay. I feel like these last couple lectures, I'm going to just kind of mention a few other data analysis techniques and methods that you can use, and it may apply to your project. You might have data where this is relevant. You might not have data where this is relevant. But here we are going to take a look at correlation and simple linear regression. And so the idea behind correlation and linear regression is that we are looking for relationships between numeric variables, okay? So the example I used is how does Zillow estimate house prices, okay? Or whatever it might be. We have to understand the relationships between these different variables or different factors, okay? So, at a very, very basic level, okay, in housing, generally, bigger houses, larger houses with more square feet come with higher prices, okay? Obviously, there's a lot more, like what neighborhood, what city you're in. If you're living in Los Angeles, it's going to be more expensive than if you live in, Bakersfield or something. No shade to Bakersfield, but the housing prices out there are certainly not as high. And so, but in Bakersfield, bigger houses will cost more than smaller houses in Bakersfield. Okay, in Los Angeles, bigger houses will cost more than smaller houses, right? But what we want to do is we want to be more precise than just saying bigger means more expensive. Okay, we want to be able to make something more specific, and that's where linear regression is used. Okay, and it allows us to quantify them by saying something along the lines of, on average, 1 extra square foot in the house is associated with an increase of $350 in the value of the house. Okay, I've just made up that number, but you can be like, okay, well, if a house is an extra 100 square feet, it might be $35,000 more than another house that's 100 square feet less, right? So if you have a 1,500 square foot house and a 1,600 square foot house, this equation or this linear regression would say, yeah, maybe the 1,600 square foot house will cost $35,000 more than the 1,500 square foot house, or something like that, right? And so that's kind of what we're going for when we do linear regression, is we want to quantify these relationships, okay? So we're going to look at how do we describe these relationships, how to measure their strength, and how do we build models to make these predictions. All right, so one of our first data sets that we'll look at is this data set from the Census Bureau. Always some kind of interesting stuff happening with the Census Bureau. But this one looks at age of first marriage, okay? So the way this data works is, every year the census says, like, okay, who got married for the first time this year? So in 2019, a bunch of people get married, okay? And for some of these people, it's their second marriage or their third marriage, okay? But for a lot of the people, it is their first marriage, okay? And then they say, okay, if we look at only the people who got married and it's their first marriage only, what was the average age, okay? What was the average age of these people? And they split it between men and women. And then they said, okay, so for men who got married for the first time, what was their average age? The average age was 29.8. For women who got married for the first time in 2019, what was their average age? Their average was 28, okay? It's not necessarily, when you see the data presented like this, you might think like, okay, this man married this woman or something like that. It's not like that, okay? You could have, because when people get married, it could be the man's first marriage and the woman's second marriage, okay? And in that case, only the man who it was their first marriage would be included in the data set. And then the person who got married, is their second marriage not included, right? It could be two men getting married, two women getting married. It could be, there's no non-binary category in this data set, but this is just how it is recorded, okay? And so they've been doing this for quite some time. I think it dates all the way back to 1890. Back then in the data set, they were only doing it once every 10 years. But they still have data for like, is this your first marriage? And if this is your first marriage, how old were you? Okay. And if you plot this, men's age of first marriage and women's age of first marriage, this is kind of what the plot looks like. And so what we see, so I think 2019 is this data point right here, where men's age of first marriage is 29.8 and women's age of first marriage is 28. And then 2018 is the year 29.8 and 27.8 is this dot right there. And these are all different moments in time. But it's just what we see is that in years where the average age of men's first marriage is kind of high, relatively high compared to the rest of the data set, it also is relatively high for women, okay? And then there were also moments in history where the average age of first marriage for men was like 22, 23 years old, okay? And women during that time tended to get married if for their first marriage between 20 and 21 years, okay? Which today just feels like, I don't know how old you are, but it's like, so many of our peers are like 20 and 21, and it's like, that's the average age, which means there were quite a few people who got married younger than that and people who got married older than that. But, on average, the average age of first marriage was like 20, 21 years old. And for women and for men, it was something around 22, 23 years old. Okay. And, throughout history, the ages have differed, but overall, we see this kind of trend. So we see there's a very strong relationship between men's average age of first marriage and women's average age of first marriage. In years where the average age of men's first marriage is high, women's average age of first marriage is also high. And then in years where it's low, it's also low for the men, it's also low for the women. And consistently, approximately a 2-year difference. So Average age of first marriage for men is around 26. It's around 24 for the women in that year. Okay, so that's one way we could look at that. Here, I've created another plot because in our data we have 3 variables, right? We have year, men, and women. So I did one plot where it's men on the x-axis and women on the y-axis. But I could also do year on the x-axis and men on the y-axis, or year on the x-axis and women on the y-axis, right? So these are some of the other plots that I've created. And we see an interesting kind of trend, okay? It's not like, if I saw this, I might have just thought like, okay, the farther back we go in time, people got married at a younger and younger age, okay? But that's actually not the trend. If you go all the way back to 1890 and 1900, average age of first marriage was around 25, 26 years of age for the men. And that was higher than it was like in 1960. So, as time progressed from 1890 and 1900 to 1960, average age of first marriage for men went down, okay? And then similarly for women, it also tended to go down in 1890. So like in 1890, there was around a 4-year difference. Average age of first marriage for women was around 22. Average age of first marriage for men was around 26, okay? And it went down until around 1960, which is where it was kind of like the lowest, 1950, 1960. And then after 1960, average age of first marriage continues to rise year after year, okay? And so the youngest when people got married was around 1960, where it was around 22, 23 for men, and around 20, 21 for women. And then consistently after 1960, average age of first marriage continues to climb and climb and climb till our last recorded year in 2019, where it's around 29, almost 30 for men, and around 28 for women there, for average age of first marriage. So just some interesting trends. At least this is in the United States. I don't know what it is in other countries, but this is the trend that we have there. Okay. So if we were to describe this relationship, we would still say there's a very strong relationship between year and the average age of first marriage for both men and women. However, if we had to describe this, a single straight line is not going to describe the trend, right? We would have to draw like a V, okay? We have to draw kind of a line going this way and then a line going that way, okay? So from around 1890 to around 1960, average age of first marriage decreases with time, and then from around 1960 to 2020, average age of first marriage continues to increase year over year. So a single straight line is not going to be sufficient there. Okay. Let me give you your first quiz answer, and today the first answer is A. A as in apple. A as in apple. All right, so we need to be able to describe relationships. And so the things that are important when we're describing a relationship are things like the shape, the trend and direction, the strength, any kind of outliers that we have. All right, so the shape, there are lots of different shapes. As far as we're going to worry about, we're going to say you can have a linear relationship or a nonlinear. Linear means the overall trend can be summarized with a single straight line. So if you create a scatter plot, you put, AES X, and, X is this variable and Y is that variable. If overall there's kind of a cloud of points and overall it looks like a straight line, you can say there's a linear relationship. And if it's not, then you would, if you need to draw some kind of curved line, you would say a nonlinear relationship, okay? There's a lot more than just nonlinear, so you can say, there's a quadratic relationship or exponential or logarithmic, and there's all kinds of ways you could further subdivide the nonlinear relationship. As far as our class is going to be concerned with, I guess at the beginning, we just concern ourselves with linear versus nonlinear. If you are interested and take more statistics courses, you can learn about these other kinds of relationships that exist. Okay, but as far as the direction of the relationship goes, we can say the direction is positive, negative, or neither, okay? For the relationship, the direction to be positive, that means large values of x go with large values of y, and small values of x go with small values of y. So x and y kind of move in the same direction. In a negative relationship, x and y go in opposite directions. Large values of x go with small values of y. Small values of x go with large values of y. Okay. And then sometimes you have a neither positive nor direct negative, and that would be, large values of x, maybe they go with large or small with y, and then small values of x aren't really associated with large or small values of y. Let me just show you a few examples of this, okay? So positive trend overall, again, large x goes with large y. So the example here is, think of how old a car is and how many miles have been driven on that car, okay? So it's like the odometer reading. And so in general, older cars will have more mileage driven on it. Newer cars will have less miles driven on it, right? So yeah, I don't know who gathered this data, but they have a 20-year-old car, okay? And that 20-year-old car has, 160,000 miles on it or something. You have, a 5-year-old car, and it's got somewhere between 50. You get multiple cars that are 5 years old with somewhere between 50 and 80,000 miles or something. But in general, what we see is that as older cars tend to have higher mileage, newer cars tend to have lower mileage, okay? We have some exceptions. We have a 6-year-old car with like 240,000 miles on it or something. We have like a 22-year-old car with only 70,000 miles on it. But in general, we have this kind of positive trend, okay? Negative trend is large x goes with small x goes with large y. And so this is looking at different countries, and they are measuring the literacy rate of that country, along with kind of a measure of fertility, which is total births per woman. And so, in countries that have high literacy rate tend to have fewer total births per woman. Countries with lower literacy rate tend to have higher total births per woman. That is the trend that we see in our data, and so that is a negative trend. Now, when you see something like this, okay, and this I have to, this is going to be a big thing. When you do your projects, you are often eager to find some kind of conclusion to make from your data. That is just our natural thing, and we want to say like, okay, we're finding this kind of trend and this kind of relationship, and these kinds of trends do exist, okay, but we have to be careful not to draw a cause and effect conclusion, okay? We don't want to say that just because people are learning how to read, that means that causes them to have fewer children, okay? Or even more, an even more difficult explanation would be like learning to read, has a biological effect that hinders your reproductive organs or something like that, right? And I mean, sometimes you hear like these conspiracy theories where it's just like, oh, there's this epidemic of, lower hormones and things like that and stuff. And we have to, avoid jumping to these kinds of cause and effect conclusions, okay? All right, so we don't want to say just because people are learning to read that causes people to have fewer children or something like that. And, you know, the different variables and factors that are at play that are related to how many children people choose to have are complicated. But certainly kind of literacy could be an indicator of, you know, economic development and access to education, and maybe people having more decision-making, you know, autonomy over decisions and things like that. And those could all play a role in the relationship that we see. But we don't want to just quickly jump to some kind of cause and effect relationship, okay? Here is an example of a relationship that is neither positive nor negative. This one, they looked at, I think, marathon times, how long somebody took to complete the marathon, how old was the runner, and we have a whole bunch of different people of different ages, and some finished quickly and some took a long time. And so you see, you know, there are young people in you know, 18, 19, 20 in this data set who took a short amount of time and took a long amount of time. There are people in their middle ages, middle-aged people who took a short amount of time and a long amount of time. There are people who are older, you know, over 60, who took a little bit and a long amount of time. So we don't really see any kind of association, okay? We can't say older people tended to take longer or less time, younger people tended to take more or less time, okay? This is also another example of a relationship that is neither positive nor negative. This is just some simulated data, but one thing here is that there's definitely a relationship between x and y, and it looks kind of like a parabola or a hyperbola being drawn here. But we can't say that the overall relationship is positive, because what we see is that large values of x go with large values of y, okay? But also small values of x go with large values of y. And it's really like the middle values of x that go with the small values of y. And so, you know, if we were to split the data right here in the middle at x equal to 0, sure, the right-hand side would be positive and the left-hand side would be negative. But if we take the overall data into account, everything kind of balances out, and we can't say, you know, as far as the entire data set goes, there's neither a positive nor a negative trend, okay? There is a trend, though, okay? There's definitely a relationship between x and y. The strength of a relationship summarizes kind of how much scatter appears in the scatter plot. And so, you know, as you describe data and things like that in your projects, you can use words like there's a weak relationship or a strong relationship. And the strength, you know, we can think of it as how well can we predict one variable based off of another. And so here are two examples, and I think they gathered data, I think from the CDC, where they measured a whole bunch of, you know, took people's measurements, and we looked at their height, we looked at their weight, we also measured like their waist size. And, you know, what we see is there's both of these have a positive relationship, okay? Taller people tend to weigh more, shorter people tend to weigh less, positive relationship, okay? With waist size, people with larger waists tend to weigh more, people with smaller waists tend to weigh less, okay? But as far as predictive power goes, you know, if you have two people with the same height, they could have vastly different weights, okay? This person is 70 inches and it looks like they weigh 120 pounds, and also 230, 260 pounds. Okay, we got basically, you know, if you pick one height here, 70 inches, you got kind of a big spread of how much you know, two people with 70 who have the same height, there could be a big difference between their weights, okay? Whereas if you look at waist size, you don't have as much spread, okay? If you have two people with the same waist size, like 35 inches, okay, on the low end, it looks like 160, and on the high end, maybe 220 or something like that. So they kind of, if you know one of these variables, how accurate can you expect your prediction to be? Okay, if you know the waist size, your prediction is probably going to be more accurate than if you only knew their height. Okay, so this is the strength of a relationship is kind of like how much scatter is there in the plot. We have more scatter over here. This is a weaker relationship. We have less scatter over here. This is a stronger relationship. And again, it's kind of just like if you know one of these values, if you know somebody has a waist size of 30, what kind of range of values can you predict? Okay, versus if you know somebody has a height of 65, what kind of range of values would you predict? And there's a bigger range there. Okay. So if we were to use that and describe the relationship here between the average age of first marriage for men and the average age of first marriage for women, we would say that relationship, there's a positive direction. The shape is linear. Okay. And we would say the association is strong, the relationship is strong because there's not a ton of scatter. It looks, you can almost see the line right there, right? So if you can draw a straight line through it and it doesn't look like there's a ton of scatter, that means you have a strong relationship. Just a couple key things that's important is that we always use the phrase things like tends to when describing a relationship or an association because the trend will always have some variability. And even if there is this overall trend, it's not going to apply to every single individual. There will always be some individuals that kind of don't fit in with the trend. Okay. If you have any kind of outliers or things that are unusual, not part of the general pattern, you should point those out. Our lecture last week talked about how do we identify some of these points that are unusual. And if you are able to investigate those individual unusual points, that often there's often some compelling information there. I think the Airbnb project that I posted as an example, I think that group did a good job because they found, these listings that were like thousands of dollars, right, per night. And they said, well, that seems really weird. And so they actually went on the website and they looked it up. And they said, oh, yeah, this is kind of like a house where, with multiple bedrooms. So that kind of makes sense. But this listing seems almost either like a fraudulent listing or something, or it was just like, here's a 1-bedroom and we're charging thousands of dollars per night. So, it just feels a little bit strange to see that, but, use their best judgment to kind of figure out and not accusing. I don't want to be accusing people of fraud, but it just, it seems like that person wasn't actually intent on renting it out or something. Okay. The value that we use to measure these relationships and describe them is the correlation coefficient. Oh, I'm running out of time. Let me give you, how many answers have I given you? 1. Okay. I'll just go ahead and give you your second and third answers. Second answer is C as in cat. And the third answer is E as in elephant. C as in cat and E as in elephant. Okay, so the correlation coefficient is R. It's always going to be a number between 1 and -1. If R is 0, you have close to 0, you have weak linear association. If R is close to +1, it's going to be positive. If it's R close to -1, it's going to be negative and strong. Okay, the sign of R. So if you have lines that are in a perfect straight line, your correlation is +1. If you have data where the correlation is +1, probably something is wrong. Okay, this should not really happen in real life data. So usually this happens if you just multiply something. Like you do a conversion factor, like what is the person's age in years and what is the person's age in months, okay? and you just take it and you multiply by 12 or something. That is how you get something like this. So usually an R of exactly 1 or exactly -1 indicates something probably I would be suspect of that thing. If you're not sure, come see me. Here's just some other kind of plots. This one has a relationship of 0.72, an R of 0.72. As you get kind of more scatter, this is 0.48. Here's even more scatter. I guess it's very minimally positive. R equals 0.19, but it looks, very, very weak relationship there. To calculate the correlation in R, you type in core, and then you take the column, the two columns that you're interested in. So here, for our marriage data set, we can do marriage $men for the age of men, and then for the age for the women, marriage $women. Correlation there is 0.985. Okay, so very high correlation, but not exactly 1. Exactly 1 is a problem. 0.985 just means very high kind of relationship. A few things regarding correlation. If you change the order of the variables, so if I did correlation of women and comma marriage $men, it would be exactly the same. Okay, so whether it's what's the correlation between age of first marriage for men and women, same as women and men. Okay, if you change the units, that doesn't affect your correlation. So if you're measuring things in centimeters and then you decide to change to inches, correlation is going to be, say, the same. Okay, if you measure in pounds and switch to kilograms, shouldn't change anything. Fahrenheit, Celsius, those kinds of things. Correlation itself is unitless. Here's the important thing, though. Okay, correlation, this R, is only useful for a linear relationship. You always have to kind of create a plot first to just make sure, does it make sense to use a straight line to summarize the overall relationship? If you see kind of like a curve there, correlation, it's just the result of a formula. So it will spit out a number, but that number is not going to have interpretation. Okay. With linear regression, we're trying to find the equation of a line. Okay, so lines are what? Slope plus intercept. Slope times x plus intercept, and that's what we have. We have an intercept A, slope times x, and that's going to be the trend line. Okay, I'm going to just call these our x variable and our y variable. We have names for these, explanatory and response and other kinds of things. But anyway, this is just like a simple example. What's the relationship between the age of a vehicle and its value? Okay, and I don't know when this data set was gathered, but it's like cars are like way more expensive today. But the idea here is you plug in the age of the vehicle. So if you plug in 10 years for the age of the vehicle, okay, the value of the predicted value of the car would be 21,375 minus 10 times 1215, and I don't know, you'd get something around, $9,000 some $100. Okay, and it's along this line. So as vehicles get older, we expect their value to go down, basically around $1,215 per year. So a 12-year-old vehicle, according to this data set, okay, 21,375 minus 1215 times 12 gives us 6,795. We expect a 12-year-old car to have a value of, I guess, $6,800. Just a prediction, again, based on this imaginary data set that's probably way outdated as far as numbers go. Okay. Here's just another kind of example I put in. What if we wanted to predict someone's height based on their weight? So you ask somebody, how much do you weigh? And they say, I weigh 104 pounds. And how tall are you? And I'm 61 inches tall. And this other person says, I'm 141 pounds and I'm 63 inches tall. And I'm just making up numbers here. We have 6 people in our data set. And here's a plot. It's really hard to see. But if you want to get your regression equation, okay, the way you do this in R is the function is called LM, L for linear model, we want to get a linear regression equation. And you do the variable that you're trying to predict. In our case, we're trying to predict height based off of weight. So we're going to do height tilde weight. So it says I'm going to try to predict height based on weight. The data come from this data frame DAT, which is what we have here. And so, in your data set, you load up your CSV file, you name it something, and then you can pick one column and try to predict it based off of another column. And here it says, okay, the intercept is 52.397, and the slope for the weight variable is 0.08595. And so what that means is that we plug in the person's weight in pounds, we multiply it by this number, and that's going to be our predicted height for the person. Okay, so it's a little bit silly, but this is what it looks like. This is if you wanted to try to add the line to your regression plot, this is what it looks like. And so here I have my data points, and to add the line, you call geom smooth method equals LM to draw a linear model line here. Okay, and it says using formula y tilde x, we're predicting height based off of weight. Okay, and so what we can see is that I could plug in 170 into this equation, right? And we could say, all right, my equation 52, my intercept is 52.397, my slope is 0.08595. I plug in weight of 170. So we're saying if a person weighs 170 pounds, according to our regression equation, we are going to predict this person is 67 inches tall. And indeed, if we look at our regression equation, this is 170 at this line right here. I go up to 170, I look at the line, and the line is right there at 67 inches. So that's what the line predicts, okay? Now, in our data set, we actually do have somebody who weighs 170 pounds, and this person in the data set, their actual height is 66 inches tall. And they are this data point right here, okay? So according to the regression equation, we predicted their height to be 67 inches. In reality, this person, their individual height was 66 inches. So there is a difference between what we predicted and what their actual height was. And that difference is known as the residual. The residual is the difference between the actual value and the predicted value. So in this case, this person has a residual of -1, -1.0085, okay? Basically just one inch shorter than what we predicted. Okay, you can plug in, you can ask for predictions in R as well. So if we have our the model as created by LM, you could call predict on the model. You have to make a little data frame of what value. So you can say predict if weight is 170 or predict if weight is 180. How tall do we predict? So 170, we predict 67 inches. At 180, we predict a little bit taller, 67.87 inches, 67, almost 68 inches, 67.88 inches, okay? And that's how the regression line works there. Okay, we are out of time. Just a couple more slides on this, but yeah, I guess you can read up on this on your own time. And again, I know you guys are working on your projects, and you might run into questions about is this the right analysis? Is this the right approach? And don't hesitate to come by and ask. I'm happy to offer my my opinions and advice there. Okay, all right. Good luck as you guys continue to work on your projects. Sign up for a slot on the week 10 Friday presentation schedule, and then sign up for a final presentation slot. All right, see you guys later.